Jai Hind, my dear students. Today we are going to start a new topic of control unit, the introduction to instruction cycles. Myself, Dr. Akhiles in Department of Computer Science and Engineering, and we will discuss the instruction cycles in detail. This subject topic is related to the Unit 3 control unit. Okay, so what is the micro operation? Micro operation, in very simple term, it accomplishes a very small task. Okay, so when we say micro operation, it is a simplest task, and that's why it will accomplish very little task. Okay, so that's why it is well known as micro operations. Now we know that we write program, and every program has certain instructions. Now these instructions involves many micro operations. Okay, and the characteristic of this micro operation is that it is in atomic in nature. That's why it is called an atomic operation. So if it is atomic operation, so there is no possibility to divide this into further. So that is the smallest executable part. So we are basically doing a functional decomposition, so breaking down the instructions into micro operations, or rather we are breaking down a program into instruction, then instruction into micro operation, and the micro operation is the smallest non-divisible operation. That's why it is called as atomic operation, right? So we, as discussed, it does very little and it is very simple. So we'll see later in the lecture that how it is very simple and how it is doing very little task. Fine. So a given program is broken into instruction, and the instructions are further broken into micro operation, and this approach is known as functional decomposition approach. Now if you see here in this diagram, this functional nature is shown from the top to bottom. So consider a program under execution. Okay, so what will happen, each program consists of multiple instructions. Okay, so there will be instruction 1, there will be instruction 2, ... there will be multiple instructions in a program that will be executed. So to execute this program, we divided program into instruction, but how this instruction is executed? So if you will see that the instruction is further divided and also known as instruction cycle. Okay, and each instruction cycle composed of multiple sub-cycles: fetch cycle, indirect cycle, execute cycle, and interrupt cycle. So this instruction cycle composed of 4 stages of executions or 4 stages of sub-cycles. And if you go down into detail of the fetch, okay, you will find that it is composed of multiple micro operations. Similarly, indirect cycle will have another set of micro operations. So when we consider a machine instruction, it is broken into micro program, and each micro program consists of micro instruction. So every instruction is first converted into machine instruction, and for corresponding micro instruction there is a set of micro program that will be executed one after another in form of fetch, indirect, execute, and interrupt, and each micro program has a sequence of micro instruction that will be executed, and this is the smallest atomic operation that will be performed. Okay, so you can see there will be many atomic operations that will be executed at the lowest level of the hierarchy in this tree structure, and when they all execute, it will complete one instruction. Likewise, for every instruction there will be same lowest level of atomic execution of micro operation that will happen in the computer. Fine. Now, if we see the flow diagram of the various units available in the computer, we can see that there are three different buses: address bus, data bus, and control bus, and a external unit memory. And within the CPU, we can see there is a program control register, there is a memory address register, there is a memory buffer register, there is a instruction register, and a control unit. So this control unit is basically directing various micro operation to be executed. Okay, so if we see the path of data that is connected to the buses, we can see that these paths are executing multiple micro operations. So if we see the category of micro operations, a single micro operation generally are of three types. Basically, it is a transfer operation, okay, and it involves register to register transfer, okay. It may involve register to some external source, okay. It may be a main memory, okay, or some IO operations. And also another type of micro operation is execution of ALU. So we can see simply there are three categories: 1, 2, and 3 subset of micro operations that a CPU can execute. So we can see here that there is a flow that is happening between various registers to bus, or from bus to register, or from register to memory, or memory to register. And if we have to execute something, the ALU which is connected somewhere here, okay, will be executing the data that will be transferred through the IR to bus, and bus to again ALU, then ALU to again to the some register. Okay, so how this is being executed within this this micro operation being executed over this organization of a CPU. So with each clock pulse that is of some definite time unit, okay, that is a time period fixed by the hardware, which is R of equal duration. So there will be another time period just after that, and so on. So for each and every clock pulse, first clock pulse, second clock pulse, and third clock pulse, these micro operations are performed within the CPU. So if data has to be transferred from MAR to memory, then it will take one clock time unit, or from memory to MBR, it will take another clock unit time. Now we can see that we can explain it with a simple analogy that these subunit PC, MAR, MBR are the sublocations, and these bus structure is a road connection. So we can travel from any subunit to any subunit through this road connection, or we can travel through bus. So if any multiple micro operations are there, will it interfere with each other while traveling over the bus? Yes, there might be some interference. So in case if there is no interference, some path is going such that there is no interference, a separate path is going here and separate path is going here. So we can group these two micro operations in the same clock period. So multiple micro operation can be grouped together, okay, within the same time period. So what will happen, in one clock there will be multiple micro operations executing, provided they are non-overlapping, means there is no conflict in the physical resources while using like bus. Okay, so grouping can be performed in two ways. First, we have to ensure that there is a proper sequence of event takes place, that is the logical sequence of the operation that is decided at the each cycle. So it cannot be like this, that this micro operation is done first, then this microoperation is done second. So there will be a sequence required. Okay, proper sequence. So first we will do PC followed by PC content transferred to MAR. Then the memory data is transferred to MBR. But we cannot do like this, that first we perform the memory operation, then we perform the PC to MAR operation. So this sequence is required. That is basically a logical sequence to accomplish a task. Second important thing is grouping is the conflict to avoid the conflict. Okay, now say for example, if we are sending some data from memory to MDR register, at the same time it is not possible that the MDR data is copied to IR. So there is a conflict of MDR, that is the same unit being used by both micro operations. Okay, it's not possible that MDR and is conflicting with the another micro operation MDR content is transferred to IR. Okay, so we must have a grouping based on the proper sequence, as well as we should avoid the conflict between the two micro operations. So to understand the micro operation, we should understand the CPU clock also. So what is CPU clock? CPU clock is a repeated sequence of pulses. So we can see here, there is a CPU clock. So we can see here, we are starting here, then we are ending here, then we are starting here, then we are ending here. So this is a time t0 of a pulse. Okay, when it has passed to this point, then the time t1 has passed. So likewise, you can see we can have up to 5 clock pulses passed, and after some time, if operation is completed, we can start again from t0 cycle. Okay, so at various interval of this clock pulses, we can perform meaningful micro operation. So at every pulses, we are basically using this pulses for performing some micro operation during that. So we must have enough time to allow signal to propagate from point A to point B during the pulse. Okay, so this is to be ensured that the clock should be long enough to propagate the signal from point A to point B. Okay, different control signals at different time within the instruction set. Now, the CPU clock plays a very important role because control unit generates control signal. Okay, and the control signals basically enables a particular set of micro operations. Okay, so different control signals are generated at different time to execute the instruction set. Okay, so how we will do that? So we will use a counter circuit that will generate different control signals for T1 and T2 etc. In this control CPU clocks. So at time T1 we will generating another micro control signal, and at T2 they will be generating another control signal. Fine. Now let's have an example. So we already know that there is a sub-cycle within an instruction, that is fetch, okay, indirect, execute and interrupt. Okay, let's see in detail how these individual cycles are broken into a micro operations. Okay, so first micro operation is a fetch cycle, is a fetch cycle, and we can see there it consists of 3 time units, T1, T2, T3. So basically if we see over the timeline, the clock T1, then there will be a time T2, okay, then there will be a time T3. So at clock when passed by T1, the first micro operation that will be executed is the transfer of content of PC register to MA. So after T1 has passed, when T2 will come, the second micro operation will be executed. The content of memory that has been requested by the time T1 has passed will be moved to the memory data register. Okay, so whatever the data is requested by the PC through MAR will now be copied to MDR. Now, since we know that PC is a program counter and it is basically meant to get the instruction, so by this time we have the instruction available in the MDR. So this register contains the instruction. So the CPU contains the instruction which it has requested through PC. Now at time T3, we have to increment the counter of PC plus 1 so that we are switching to a new program counter. And also, since the MDR contains the instruction, the content of MDR will be moved to the IR, that is the instruction list. So basically in fetch cycle, we send the program counter having address for referring a particular memory location for an instruction. When instruction is available in MDR, it is now available in the CPU. So PC content is increased by 1, and we have copied the content of the MDR, that is the instruction, to IR register. So fetch cycle has completed. Now when fetch cycle is completed, what we will do? We will go for the second cycle, that is indirect. Okay. So in indirect, basically we now have the instruction. So after getting the instruction, it might be possible the instruction may be a having addressing mode indirect or direct. If it is direct, we do not require to go again to the memory location to fetch the data. If it is indirect, the IR will have a copy of address, isn't? And that address is now moved to the MAR. Okay, so memory address register will send data to the memory that please bring this particular data because it is an indirect operation. So in the memory, data will be read and copied back to the MDR. Okay. Now this MDR will contain the value of that particular memory location. Fine. Now this value is copied back to the IR. Okay. So basically at this stage we are getting the address to the MAR, and at this stage we are getting the value of that particular address in IR. Now this IR has the actual data available to execute. So certainly when we do a fetch, instruction is available in the CPU, and the CPU control unit will check whether it is a direct or indirect. If it is indirect operation, this indirect cycle operation will take place to bring out the data from the main memory. Since the data is not readily available in the instruction, it is an indirect operation. Okay. Now, before we execute, there is an important cycle that is needed, that is called an interrupt cycle. Okay. Many times the instructions are enabled by interrupts for the occurrence of certain outside event. Okay, so if interrupt is enabled, the interrupt cycle will basically perform the saving of the current program counter to the MDR, and this will be saved, okay, through MAR, and the saved address will be sent to the MAR and copied to the main memory. Okay, and due to the interrupt, whatever the routine address has been generated, it will be copied back to the PC. Okay, and since the new address is updated to the PC, so what will happen? We will copy the at T3 step the MDR content to the memory. So basically the content of PC are transferred to MDR so that they can be saved for return from the interrupt when we come back after servicing the interrupt. So MAR is loaded with the address at which the contents of the PC are to be saved, this one, and now PC is loaded with the address of the starting point of interrupt routine, and the final step is to store the MDR into memory because we have to save it into the main memory. So this cycles may happen in case interrupts come. So it is optional, it is not mandatory that interrupt cycle will come, and interrupt cycle is done after the execution step. So first step, second step, third step will be done, then there will be a checking by the CPU control unit that whether there is an interrupt or not. If interrupt is there, then it will check the current, save the current PC and execute the new routine and come back to the same position because it has already saved it in the main memory. Now, final step for the execution of a complete instruction is the execution cycle. So, we know that at time t, IR contains the instruction register. So it will take the address part to the MAR and it will get the data from the memory to the MDR. Now the data is available in the MDR, and if the instruction is like add R1X, what does it mean? It means that we have to add the content of R1 with the memory content X. Okay, memory content X and store the result into R. Okay, so since IR is having direct address available, so certainly we do not require to perform an indirect operation. We will send that address to the MAR, bring the data from the memory to the MDR. Now data has the value of X here. Okay, value of X here. So value of X plus R1 is stored at R. Fine. So we understand that first we have to fetch the instruction, bring that instruction to the IR. Then if it is an indirect operation, then certainly we have to bring that data into the IR through indirect operation cycle. If we have an interrupt after execution, we have to execute the interrupt cycle. Finally, when we have to execute, if there is a direct instruction, we have to bring data from the memory to the MDR, then MDR content is added to the R1 content and the result is stored in the R1. So, if we see the system of control unit, we can categorize these 4 cycles as 0, 0, 0, 1, 1, 0 and 1, 1, 4 cycles, and we can plot a diagram for the cycles. So we can see here, we are starting from here and we can move to any of the steps in the cycle. So first is the fetch cycle. If fetch is executed, fetch the instruction. If indirect cycle happens, because there might be chances that indirect is there. If indirect is there, so we can go to 1, 0 and 1, 1 operation. Okay, 1, 0 and 1, 1. Okay, so if indirect cycle is completed, then we will again go to the same position. Okay, and if execution is to be done, then we will move to here. Then opcode will execute the data, and if interrupt is enabled, it will serve the interrupt. Okay, and if it is not enabled, it will directly execute and start from 0, 0 again. So dear students, we can have some interesting questions that can be asked from this topic, like a single micro operation generally involves, okay, that we have discussed in start of the lecture. It is basically a transfer between register and external device, or it is a AKGEC operation. 3 types of operations are there. Can we group micro operation? Yes, we can group logically. We have seen here. Okay, and also we can have various implicated questions related to the flags and what is the hardware implementation. Okay, how many cycles are there, and is there cycles variable? Yes. So we practice these questions for this particular topic. Jai Hind.